Hello, welcome to Project 152, the weekly specialist exam prep. So every week we take a look at some past QCAA external exam questions to prepare us for our external exam at the end of the year. If you follow along with this for the whole time, you'll have done every single question, all 152 of them that the QCAA have produced. Alright, if you didn't watch last week's video, go and check it out. I explain it all there. I also provide you with this week's questions. Now, if you go into the description, you'll see next week's questions, and you can start working on them throughout the next 7 days. All right, let's go into our first question. This is an absolute classic. It's proof by mathematical induction. This sort of question, this style, seems to pop up every year. All right, so we have our proposition, and the proposition is that this formula here is true. So that's a partial sum. We're summing this thing here, and that formula is a faster way to get there. Okay, which option represents a correct formulation of the assumption PK? This happens a lot, and students find this difficult because we learn proof by induction as like a big long list of steps, but a question like this just says, hey, just do one small step here. All right, so what are we trying to write down? We're trying to write the assumption that PK is true. All right. Now, what is the proposition? The proposition is Pn. Okay. Now, when we're trying to assume that PK is true, all we're doing is putting K into our equation wherever we see the letter N. That's it. So, R equals 1. Now, we can see here, there's the letter N there, so I've got to put K there. Alright, then we have R plus 1, times 3 to the R minus 1 equals N, okay, so not N, K, times 3 to the K. Okay, and then all that other junk, but we don't have to put that in there because it's not in any of those options. All right, is what I've written appearing in any of these? Yeah, I think I can see it. Option C looks identical to mine. What mistake do people make in this question? The major mistake that people make in this question is getting too excited and thinking that they should just put K everywhere. They should just put K in here for the R, K here, K, just K for everything. Not the case. If we're trying to prove, if we're told what our proposition is, Pn, and then we're told what it is, if we're trying to assume that it's true for K, that just means we're putting K in just for N. So I think a lot of people maybe give an answer that looks like option A, where everything is a K. Not it. All right, that's our first question. 4 more to go. I feel like every question deserves one of these. Okay. Now, a lot of you might have looked at this question and asked your teacher about it, and they said, well, we haven't done complex numbers yet. Don't do the question. I disagree. You did complex numbers in Unit 2, so you're very capable of doing this question. If you didn't do it, you should pause the video now and just try it for yourself. You should be able to do it with your Year 11 knowledge. Okay. So it's really just plug and play here. We're told that Z equals 2 minus 2i. I like to put a little thing there for my Z. We're told that W is equal to negative 3 plus I. And then we're asked to calculate Z squared. Let's write it here. Z squared minus W with a hat on it. And W with a hat on it means the conjugate of W. Okay. So, what's Z squared? Well, Z is 2 minus 2i, so 2 minus 2i times 2 minus 2i. 2 minus 2i multiplied by itself, minus the conjugate of W. Now, W is negative 3 plus I. If you want to write the conjugate of it, all we're doing is changing the sign of the imaginary component. So that negative 3 will remain negative 3. But this is not positive I anymore, it's negative I. So, got to be a bit careful here because we're subtracting this. Alright, subtracting negative 3 minus I. Okay, so FOIL method here. 2 times 2 is 4. Outer 2 times negative 2i is negative 4i. Negative 2i times 2, also negative 4i. This pattern always pops up when you square complex numbers. And then negative 2i times negative 2i is positive 4i squared. We'll talk about that in a second. And then negative 3 minus I. Okay, the time has come. We have negative 4i minus 4i, which is negative 8i. And then it's this thing here, which always happens when you square complex numbers, 4i squared. Now, I times I is negative 1, and positive 4 times negative 1 is negative 4. That always happens. It happens so often that you should probably just be able to do it in the first stop. Negative 2i times negative 2i is negative 4i squared, which is positive 4i squared, which is negative 4. Okay, negative 3 is positive 3, and negative I is positive I. And then we're just grouping terms, that's it. So 4 minus 4 is 0, plus 3 is 3, and negative 8i plus I is negative 7i. Gee, I really hope that's an answer. I can see it. The answer is B. Alright, I told you could do that. I will be putting some complex number ones into the next couple of weeks, even though many of us won't learn it till like week 6 or week 7 of this term. Maybe you've already learnt it, you're all doing different things in different orders, but you can do it. Okay, next question. Alright, so here's our question. Some of us may not have done vectors yet, but gee, you should still be able to do this question. So they're asking for the position vector, I'm going to mention that, we're going to talk about that, representing the midpoint of AB. Alright, position vector. A position vector is a vector starting at the origin and going to a place. What is the place? The position vector representing the midpoint of AB. Alright, so the midpoint of AB, this is A, this is B, so this is AB. The midpoint of AB is exactly what you would think it is. It's right there. The position vector representing the midpoint AB is the vector that starts at the origin and goes there. Alright, so I've drawn a little bit on here. Don't need this, don't need this. Alright, so a position vector is really just the point. That point right there, right? Now, you just got to do things in the right order. This is our x-axis, this is our y-axis, and this is our z-axis. So, you can see B is here and it has an x-coordinate of 10. A is here and has an x-coordinate of 0. The x-coordinate halfway between 0 and 10 is 5. That's the x-coordinate of our midpoint. We can do the same game the whole way through. So A has a y-coordinate of 5. B has a y-coordinate of 12. Halfway between 5 and 12, we can add them together, that's 17, divided by 2, 8.5. Okay, and then finally the midpoint of this one, well, B is on the ground, so it's got a z-coordinate of 0. A has a z-coordinate, it's way up in the sky, it's 20. So halfway between 0 and 20 is 10. Alright, my answer is A. Now, that is not the way that I've done it here is probably not like the traditional way of doing a question like this. But when it comes to multiple choice questions, you should feel comfortable just doing whatever you should do to get to the answer the fastest, right? Traditionally, if you were going to do this question, it might look something a bit more like this. The midpoint of AB, we can use like the midpoint formula for that, which is half of OA plus OB. Now those are just the position, these are just the position vectors of A and B. The position vector of A is 0, 5, 20. The position vector of B is 10, 12, 0. If we add them together, we get half of 0 plus 10 is 10, 5 plus 12 is 17, and 20 plus 0 is 20, and half of that is 5, 8.5, and 10. Same answer. Do I think this working, when they're going to give me a picture like that, this kind of way of working is better than this way of working? Yeah, I do, but whichever one works better for you. All right, that's our third and final multiple choice question. We've got 2 short responses. All right, so here we have another vectors question. Now, part A, all of you can do. If you haven't done something called the vector product yet, or equations of planes, you're going to struggle with the other bits. All right, so let's get it started. State the coordinates of A, B, and C. All right, super easy. We ran through this in the last one. X comes out of the page, Y that way, and Z that way. So this is point A. So its coordinates are 1 this way, 3 this way, and it hasn't gone up at all. So A equals 1, 3, 0. B is way up here. Now, it hasn't gone out of the page, so 0, but it has gone across 3, and it has gone up, and it's gone up by 2 units. So 0, 3, 2. And then finally, we have vector, or point C, which is 1 this way, nothing across, but then 2 up. So C equals 1, 0, 2. All right, that is part A. It is worth 1 mark. Now, bit hard in the externals. If you make a single mistake here, you're not getting that mark. So you've got to get all 3 of those correct. All right, so part B is the next one. Determine a unit vector that is normal to the plane containing A, B, and C. All right, so we have 3 points, A, B, and C. And then imagine you had a piece of paper, right? And all 3 of those points were on that piece of paper. So we're kind of taking the piece of paper and kind of cutting a slice through that cube, that rectangular prism that we're looking at. That's the plane. And then jutting out of that plane is a vector that is at right angles to the plane. Now, if we have one vector and we have another vector and we want to draw a third vector that is perpendicular to both of them, we should be thinking about something called the cross product or the vector product. And that is exactly what we have here. So we can choose any vectors to work with here. I'm going to go with vector CA and vector CB. Okay, so there is CA there and there is CB there. And we're going to find the vector that is at right angles to both of them, right? Jutting out of there somewhere. All right, so first of all, I need to know what vector CA and vector CB are. So if you want to find a vector connecting 2 points, it's going to be the position vector of the second letter, A, so 1, 3, 0, minus the position vector of the first point, so OC, 1, 0, 2. All right, so CA is going to be 1 minus 1, which is 0, 3 minus 0, which is 3, and 0 minus 2, which is negative 2. Okay, you can also, because we have a nice picture here, we can also double check that that's true. Okay, so starting from here, do we go out or inwards to go to A? No, we don't. So 0 is correct. 3, we go 3 across. There's our Y, so yes. And then minus 2, 2 down. Yeah, to get from there to there, we do that. Now, using an identical procedure, I can find vector CB, and that is negative 1, 3, 0. Okay. So far, so good. Now, to find that vector that's at right angles to both of them, I do the cross product. So I do vector CA times vector CB. And I might just write that as 0, 3, negative 2, and negative 1, 3, 0. There are my 2 vectors, and I'm going to multiply them by each other, the cross product of them. Formula sheet. There it is, cross product on your formula sheet. Now, don't bother memorizing it, just do what it tells you to do. So it says do A2, B3, so 3 times 0 is 0, and then minus A3 times B2, so minus 6. So that's going to be positive 6. Now the next one says A3 times B1, so negative 2 times negative 1, that's 2. And then subtract A1 B3. All right, so that's 0, so then that's just 2. And then the last step is A1 B2, so 0 times 3, which is 0, minus A2 times B1. So minus 3, which is 3. We get 6, 2, 3. Now, what is 6, 2, 3? That is the vector that we want that is perpendicular to A, B, and C, or at least normal to the plane containing A, B, and C. Same thing. Now, part B didn't ask us for the vector, it asked us for a unit vector. So it doesn't just want 6, 2, 3, because that's quite a long vector, it wants the unit vector. So, the unit vector of CA times CB. Now, to find a unit vector, we do 1 over the magnitude of our vector. Now, the magnitude of this vector, let's find it. The magnitude of the vector is 6 squared plus 2 squared plus 3 squared. And if you take a minute to calculate that, you'll get the square root of 49, which, delightful, is 7. All right, so there is our magnitude. Now, let's go back to our unit vector. That's 1 over the magnitude, 6, 2, 3. So we take our vector and we multiply it by 1 over whatever the magnitude of it is, and that gives us our unit vector. That's beautiful. We've created a tiny little vector that pokes out of here with a length of 1 that is at right angles to both this one and this one. That is part B done. 3 marks, starting from here, I guess, and coming down to here. The next one says verify that n is perpendicular to vector AB. Okay. We actually haven't calculated vector AB yet. So in order for us to do that, we really need to look at what AB is. AB is equal to, and we know how to find this, B minus A. All right, so let's just do it. 0 minus 1 is minus 1. 3 minus 3 is 0. And 2 minus 0 is 2. Interesting. Now, what are they telling us to verify? Verify that this is perpendicular to this. Aha. Think back to year 11, right? 2 vectors are perpendicular if their dot product is 0. Hopefully you remember that. All right, so if I do the dot product of these 2 vectors, I'll be in business. So let's try it. N dot product AB. Now that's going to be equal to whatever n is. Now I'm going to write that as 6 over 7, 2 over 7, 3 over 7. Bit ugly. Dot product, negative 1, 0, 2. And in fact, I'm going to change my mind about writing it like that, but I really want to write it for you to show you that, like, okay, that's a dot product. But the properties of dot products tell us that we can actually just do 1 over 7 times the dot product of this, 623, negative 1, 0, 2. And we're going to get the same answer. These are equivalent. Okay, now to do a dot product, we put this 1 over 7 out the front still. And to do this dot product, it'll be 6 times negative 1, which is negative 6. 2 times 0, which is 0, we add that on. And 3 times 2, which is 6. Okay, 1/7 of 0 is 0. The dot product of the 2 of them are 0. And I'll put a little therefore perpendicular. Whew. Okay, that is part A, B, and C. We still have to do part D. Determine the Cartesian equation of the plane that contains A, B, and C. I'm going to get rid of some of this just so I can make it happen. What do I need to determine a Cartesian equation of the plane? Well, I need a vector that is normal to the plane. And I can use this one here, because that vector is normal to the plane. I could also use this one here. So either of those would work just fine, but I'm going to use that one there, which means I think that I can just kind of get rid of all of that. All right, so we'll start from here. So what is the equation of a plane? Well, the one that I keep in my head, it's also on your formula sheet, is r dot n equals a dot n. Okay, so looking at each of those in turn, R is just literally any and all vectors, right? And we just leave it as R. Dot n. What is n? It is the vector that is normal to our plane. And we found that, 6, 2, 3. What is A? Now, A is a point on our plane. And what point could I choose? Well, A, B, and C are all on the plane, so I can choose literally any of those points. I can choose this one, or this one. Just feels like I should use A, just because like it's the first letter of the alphabet. All right, and then dot product, that normal again, which is 6, 2, 3. Okay, I like that. I feel like that's fine. Now this r dot 6, 2, 3 stays how it is for a second. Something will change, and then this dot product here. So 1 times what's that supposed to be? A 6. 1 times 6 is 6, plus 3 times 2 is 6, plus 0 times 3. So 6 plus 6, 12. Okay, but so I could stop here if part D said determine the vector equation. This is the vector equation. But it doesn't say determine the vector equation, it says determine the Cartesian equation. The way to determine the Cartesian equation is to replace our R, this any and all vector, with just x, y, and z. Now when we do that, that has the effect of just being 6x plus 2y plus 3z. It happens every time. 6x plus 2y plus 3z equals 12. Okay, that is the Cartesian equation of the plane. That is it. That is question 12. Now I will tell you, question 12 is generally considered to be an easy question, but this was 2020, which was a notoriously difficult exam. So if you felt okay with this question, you should be feeling pretty good about yourself. Let's celebrate. One last question. Last question here, and probably one of the easiest question 16s I've seen. Use mathematical induction to prove that 2 to the 2n plus 3n minus 1 is divisible for 3 for all positive integers. Okay, so what are we required to prove? Required to prove that 2 to the 2n plus 3n minus 1 is divisible by 3. All right, the first thing I will do, and I encourage you to write things like this, is the base case. Let n equal 1. Okay, so when we let n equal 1, we get 2 to the 2, 1, plus 3 times 1 minus 1. And that is going to be 2 to the 2, which is 4, plus 3, which is 7, minus 1, which is 6. 6 is divisible by 3, therefore true for n equals 1. And we have proven it for our base case. So now that we've done our base case, let's do our inductive step. All right, so our inductive step starts by assume true for k. Now, how do we assume that it's true for k? Well, a way that I like to assume that it's true for k, because people have different ways of working here, is to say 2 to the 2k plus 3k minus 1 is equal to 3q. Right? Now, what does that say? That says that if you put a k in here, it will be equal to 3 times some integer. If you want to be fancy, right, q is in the set of positive integers. All right, so that's what I'm assuming it's true for. And now that we've assumed that it's true, it is required to prove that it's true for k plus 1. Okay, so required to prove true for k plus 1. What I like to write here is a statement to say the thing that it's required to prove. So the thing that we're trying to prove is 2 to the 2k plus 1 plus 3 times k plus 1 minus 1 equals 3p, where p is in the set of positive integers. So we're just saying, hey, it's required to prove that it's true for k plus 1. We're saying if that is true for k plus 1, then it's going to be equal to 3 times some integer. And then I just break this up into left-hand side, right-hand side. So 3p, and left-hand side 2 to the 2, k plus 1, plus 3, k plus 1, minus 1. Okay, starting now, you look for opportunities to sub your assumption in some way into here. And I've seen this done in lots of different ways. So I'm just going to expand this before I start. So it's going to be the same as 2 to the 2k plus 2 plus 3k plus 3 minus 1. Okay. I'm seeing something interesting here. Okay, I'm seeing something interesting. It's this 2 to the 2k plus 2 that interests me, because that is the same as, and this is not always immediately obvious, so let's move this up to here so we can see what's going on. 2 squared times 2 to the 2k. That is equivalent to that. Right, because of your index laws. So 2 to the 2 times 2 to the 2k is equal to 2 to the 2k plus 2. Oh. Okay, and then I have this plus 3k, which I see here, plus 3k. And I'm just noticing something, so I'm going to keep this minus 1 on this side, and then a little plus 3 here. So it feels a little odd to do that, but what am I noticing? And this is something that I've sort of been looking at, keeping an eye on, is this whole bit here, right? All of this assumed true for k. Because all the time we're working, we're looking for an opportunity to put this into this. And what I'm seeing is a 3k minus 1 and a 3k minus 1, right? And so what I can do is rearrange this in any way I want to. So I'm going to rearrange it to say 3k minus 1 equals 3q minus 2 to the 2k. So when I write that out now, I'm going to get 2 to the 2 times 2 to the 2k, and then this 3k minus 1 I'm going to replace with 3q minus 2 to the 2k. And then I'm left with this plus 3 at the end. Okay, that might feel a little odd now, but I'm seeing another opportunity, right? 2 to the 2 is 4. So I've got 4 times 2 to the 2k, but then I've also got minus 2 to the 2k. Okay, and then I've got this 3q, and then a plus 3. All right, so this is divisible by 3, this is divisible by 3. What's going on here? 4 groups of 2 to the k minus 1 group of 2 to the 2k. That's 3 groups of 2 to the 2k. Beautiful. So what I have is 3 groups of times 2k plus 3q plus 3. I can factorize this as 2 to the 2k plus q plus 1. K is an integer, q is an integer, 1 is an integer, therefore all of this is an integer. And I can sort of write this over here. 2 to the 2k plus q plus 1 is in the set of positive integers. And then I can just say, well, alright, well, I'll just let it equal p. Now the fact that that's equal to p, equal signs everywhere. Left-hand side, we've finally found it to 3p. We can say that the left-hand side is equal to the right-hand side. So it's been proven. And we can come up with some kind of like proof by induction statement if we like. True for n equals 1. If true for k, true for k plus 1, therefore true for n greater than or equal to, or n z positive in the set of z positive. So something like that. Now I imagine there are a lot of different ways to do this bit, but it's really finding an opportunity to put that into there and making sure that you're not breaking any algebraic mistakes in the meantime. All right, we can celebrate that. All right, that is it. That is the first set of 5 questions. 152 minus 5, that is 147 questions to go. If you look in the description, you will see a link. Click the link. You can see next week's video questions at that link. You've got 7 days from today to attempt those questions. There should be about 5 of them. And I will see you this time next week to go through the answers, figure it all out. All right, catch you then.